So just as any other equilibrium constant, the constant is affected by temperature. And the reason I crossed it out is because we are not doing a temperature dependent experiment here. So we're not going to see that effect. And the equilibrium constant is also dependent on solvent, what kind of solvent we use. Some solvent polar, some solvent is non-polar. Maybe this structure is more stable in polar solvent. Also, we look at the electronic nature of the R groups. If we replace those carbon with a different R group, or we place the R group with some steric nature, so larger, very large R groups, they're gonna affect the stability of each tautomer and the substitution at the alpha carbon. So what about the substituent to this carbon here? So we are going to use the different molecules, different solvents to explore how they're gonna affect the equilibrium constant. On Canvas, I provided 20 NMR spectrons from different compounds, and it's 5 different compounds, and 4 different solvents are used for each compound. So total, that's 20 spectrums. I want you guys to analyze all the spectrums and figure out the equilibrium constant for each of them, and then you may find out the chain of the effect of the solvent, the structure, and the substituent to the alpha carbon. Canvas, there is an experiment video and procedure, and make sure you download SpinWorks. If you didn't download it from the first lecture, I provided another link in this module, experiment 4 module, and the data set is also on Canvas. And if you have downloaded SpinWorks, you can download the data from Canvas now, and I'll show you in a few slides how to process those data. You can use Spartan. So when you have the spectrum, if you have difficulties in figuring out what the peaks are, you can use Spartan to help you. You can build that molecule, and you can calculate the NMR peaks in Spartan, and then you can match your result with the experiment result and help you to identify the peaks. This is a little bit about how NMR works, and some of you guys are taking or took Chem 133 instrumental analysis before, so probably you have seen similar schematic about the NMR. So basically, it's a set of a control system that's to generate a radio frequency signal. And that goes through an amplifier, and that puts the current into the probe. And you will see a very large container that essentially is just a center tube, but that center tube is immersed in liquid helium. So it has 2 jackets in that big container. The outside jacket, well, the very first jacket, so the empty area between the purple and the outside, that's vacuum. And then the purple is a liquid nitrogen. So liquid nitrogen is very cold. At 1 atmosphere pressure, I think the boiling point of liquid nitrogen is something around 70 to 80 Kelvin, roughly minus 200 degrees C. That's very cold. And then the liquid helium is inside liquid nitrogen. The purpose of liquid nitrogen is to make sure the temperature of a liquid helium is low, and that the evaporation of helium is relatively low. Okay. So the boiling point of liquid helium at 1 atmosphere pressure is roughly 2 or 4 Kelvin. So that's extremely low. At the extremely low temperature, the current, electric current applied in to your sample that will create a pulse of a magnetic field. So when that magnetic field is created around your sample, the magnets inside the sample, that's usually caused by the proton, feel that external field and all align up to one direction. And after that field, because that's a pulse, right? It's not a constant field, it's a pulse. So when that pulse disappeared, the internal magnetic field will gradually decay away. So we will have a free induction decay signal like that. So it's starting high and gradually decay. And if we do a Fourier transform in terms of that data, that's a mathematical operation. The horizontal axis is time. The vertical axis is intensity. So this is the free induction decay real-time data. We're going to measure the intensity decay over time. And the Fourier transform is a mathematical operation that can transform the time data to the frequency domain. So that will be, the horizontal axis will become frequency, which is the chemical shift. And the vertical axis still the intensity. And once we have that transform, then we can see the chemical shift of the compound. So if you can open up the data on Canvas, open your SpinWorks and use SpinWorks to open the data. Basically, the data will be labeled by the chemical. So this is acetylacetone, and it's in benzene. So, but that's a deuterated benzene, okay? And then you look through that folder looking for a file called I5D, free induction decay. And when the file is loaded, you should see raw free induction decay data. So it's similar as I showed in the previous slides. And then you click on the processing and select window plus Fourier transform plus phase. And then it should give you a regular NMR data. And then very important step, you need to calibrate your spectrum. We use TMS as the calibration chemical. So you need to find the TMS peak. That should be around 0. So in this case, it's at minus 0.05 roughly. And I look for that peak, click on it and 0 it. So that will calibrate the location of all other peaks. And then you use the integrate feature here. And once you click on that and select the either side of the peak, they'll give you the area under that peak. So this will be a group report. I want you guys to work as a group and one report per group. In your results section, you do not need to include all spectrums. Probably need to show one indicating how you find those peaks, and the remainder can go in the appendix. Okay, and in the appendix, all peaks must be assigned. Okay, and I include a couple literatures on Canvas. You can see how those literatures are organizing their data and organizing their data table. So in the results section, I want you guys to organize your data well into a table so that looks neat. And I want you guys to spend some time looking at the literature values. Your results should be similar to literature values. And remember in homework 2, I asked you guys to look for some literature in the NMR study of tautomers. You can use those literature as reference. You can use those literature values, or you can use similar format for your report. And when you fill up with your NMR samples, make sure you fill up the solvent to 4 to 5 centimeters from bottom of the tube. Don't fill too much, there'll be a waste, and don't fill too little amount. If you fill just a little bit amount to cover the bottom of the tube, then your signal will be very weak and won't be able to give you a good result. A good result means a very good signal to noise ratio. So in this case, your signal is weak and the noise is still as usual because you have electrical noise and the noise from the environment. So the noise stays the same, but the signal is a lot weaker. Then the signal to noise ratio is not that great compared to when you fill up to 4 to 5 centimeters here. All deuterated solvents are classified as a flammable, irritant, harmful, and acute toxin. So be careful to use those solvents. We use TMS as our label of zero chemical shift. It's a very toxic chemical. It's volatile and must be kept in an airtight container. When you are not using this chemical, make sure the container stays under the fume hood. Okay, goggles, lab coats, and gloves are required throughout the experiment.